Alright, gang, here we go. So this is Physics, Unit 3, Part 5, Collisions. So this is it. We're almost done. We've talked about lots of different things in this unit, but this is the last bit. We're going to talk about momentum, how it's conserved, and we'll talk about two different types of collisions. Alright? So imagine this. You've got two girls that are on rollerblades, right? And they're facing each other. Imagine that they weigh exactly the same, like for whatever, like they're twins, right? They're just, I know they don't look like twins in this picture. Let's just assume that they're twins and they weigh exactly the same, okay? And then, so they put their hands on each other and they both push equally hard against each other. Okay, you know from force diagrams that the force exerted by one, this force here, from the force of the green girl, we'll say green, is going to be equal and opposite to the force on from the red girl, right? The green on red versus the red on green. Okay, so anyway, so these two forces are going to be equal to each other, and because their masses are exactly the same, you should know that their momentum will be the same. So therefore, their velocities will be equal to each other. However, they'll be opposite, right? The girl in the red will be going to the left, and the girl in the green will be going to the right. Okay, so that's pretty easy. You can imagine that happening pretty readily. What would happen if the girl on the right or the girl in the green had a higher mass? What would their velocities look like? Well, you could easily imagine that the girl in the green her velocity would be lower. It would still be opposite of the one in the red, but it would be lower. She'd be moving backwards at a slower velocity than the girl in the red. Okay, and then the last one, how would your answers change if the girl on the right was moving towards her friend before they started pushing? Well, that would give her a greater force pushing here, right? And so probably what would happen is the girl in the green would probably move faster to the right. The girl in the red might end up going to the left, but probably at a slower value than she was before. Okay. So this gives us to this idea of what happens to momentum during collisions. So if we have these two bumper cars, okay, and this bumper car is going at some initial velocity, all right, to the right, and then the one on the left is going faster, okay, some initial velocity, and they've got two different masses. Okay, we know that when they collide, their forces are going to be equal and opposite to each other, right? F1 is going to be equal to F2, but the one will be the negative of the other because it's facing the opposite direction, and they're vectors, right? So you have to give them the direction. Now, because they're going to be equal and opposite, therefore the momentum of one is going to be equal to the negative momentum of two. Okay. And so that happens when they collide with each other. So the change in momentum for one object is equal and opposite to the change in momentum for the other object. Okay, all right. So that's really the idea of what happens to momentum during collisions, and this is the big takeaway here. Okay, when you have a collision, your momentum is neither gained or lost during a collision. So no matter what happens in your collision, whether they stick together or bounce off each other, your momentum is conserved. It's neither gained nor lost, okay? You need to memorize that, tattoo it on the back of your hand so you never forget it, okay? So here's the formula for the conservation of momentum. So remember, momentum is P is equal to M times V, all right? So really what we've done is we've taken the momentum initially for object 1 plus the momentum initially for object 2, and that's going to be equal to the momentum final of object 1 plus the momentum final of object 2. Okay, or the total initial momentum is going to be equal to the total final momentum. Okay, so the total momentum remains constant during collisions, period, end stop. Okay, so anyway, if one object loses momentum in a collision, then that means the other one has to gain that momentum during the collision, so on and so forth. So really this idea that the momentum is conserved makes these problem solvings pretty easy, okay? Now you do have to make sure you keep track of all these things. That's why we have all these subscripts and variables to make sure we keep everything straight. Okay, so let's think about this real quick. If we have a 62 kilogram astronaut on a spacewalk, right? So he's out there, there's microgravity, okay? So essentially no gravity, he's just out there floating. He picks up a baseball and he throws it at 26 meters per second just out into space. He's like, I don't want you baseball anymore. It's going to be gone forever. What speed will the astronaut recoil, right? So he throws that baseball, and like if you've ever tried to, throw something, right, when you're like ice skating or so. I assume none of you guys have been to space, but if you're ice skating and you throw something, you're gonna start sliding backwards, right, a little bit. Okay, so that same thing happens to our astronaut. He throws that ball out there, he's gonna start moving backwards. Okay, so we need to find the initial momentum of both the astronaut and the baseball. Well, because they're both not moving, right, then their initial momentum has to be 0 because their initial velocity is 0, because momentum is equal to mass times velocity. Okay, so all right, then we have to find the final momentum here. So we've got the initial momentum is equal to 0. Now we know that the momentum has to be conserved, so that means if we define the astronaut as having a positive momentum, then the baseball has to have the equal and opposite momentum here. So the astronaut final momentum is PF, and then therefore the baseball has to be the opposite of that. Then all we have to do is substitute these guys into our initial equation over here. Okay, plug all those guys in, and we'll find that the answer to our final velocity of the astronaut will be equal to that, or he's going to go negative 6.08 centimeters per second backwards. Now notice that this is significantly lower velocity than the baseball. The baseball is traveling at 26.0 meters per second out into space. The astronaut's quite the arm, it looks like, but the astronaut's only going to go backwards at negative 6.08 centimeters per second. Okay, and the reason for that is because the astronaut weighs significantly more than the baseball does, right? Their momentum is conserved, but because the mass of the astronaut is so much higher than the mass of the baseball, the velocity has to be a lot lower to compensate. Okay, now just hypothetically, if you were a pitcher on a baseball field and you were throwing that same baseball, would you have like that backwards velocity when you do it? The answer is yes, but no, not really, because the idea is you've got friction on the ground, right? There's some sort of backwards frictional force that's keeping you backwards. So yes, there would be that force pushing you back, but because your feet are on the ground, you wouldn't be thrown backwards like helplessly like the astronaut. Okay, here's another one. So Gerard is a quarterback and Tyler is defensive lineman. So says Gerard's mass is 75 kilograms and he is at rest. So he's just kind of standing there. Okay, so here's our defensive lineman. Okay, there's his shoulder pads and he's just kind of chilling there. He's like, all right, come and get me. Okay, and then so that's Gerard. Okay, and then Tyler is going to come in here and is going to oh, Gerard's the quarterback, my bad. Gerard's the quarterback, right? So he's got the ball. All right. And then I'm going to get that quarterback. So he runs in, okay, and he's going to get him. He's going to tackle him, right? And he's moving this way. Gerard only weighs 75.0 kilograms, and Tyler weighs 112 kilograms. He's a big kid, all right? 112 kilograms, and he's moving at 8.25 meters per second. All right, when he tackles Gerard and they hold on while they fly through the air, with what speed do the two players move after the collision? So we know that the P final has to equal P initial, okay? Or P initial has to equal P final. So let's find the initial momentum here. So we've got two guys. We've got Gerard, so the mass of Gerard times the initial velocity of Gerard, so we'll call that GI, okay? And that's going to be added to the mass of, what's the other kid's name? Tyler, times the velocity of Tyler initially, okay? And so what's this going to be equal to? Well, that's going to be equal to the mass of Gerard was 75 kilograms, right? 75.0. And the velocity of Gerard is 0. He's at rest, right? So that's going to be 0. So that's all going to go away. And then the mass of Tyler was 112, and his velocity was 8.25. All right, so the initial momentum is going to be all whatever Tyler brings in, 112 times 8.25. So we get 924 kilograms times meters over seconds, kilogram meters per seconds. Okay, so that's the initial momentum there, 924. All right, so that's the initial. So we know that has to equal the final momentum. Now let's think for a second. So this was our initial, but it says they hold on while they fly through the air together. Okay, so that means the final momentum is going to be mass times velocity, but our masses are going to be combined, right? The mass of Gerard plus the mass of Tyler, they're going to be combined because they held on to each other when they hit. Okay, and so that's going to be times whatever the final velocity is of this new joint mass. Okay, so we know that 924 equals the final momentum, which had to also equal the initial momentum. So 924 has to equal mass of Gerard was 75, and the mass of Tyler was 112, and then the final velocity is whatever it is. So we'll take 924 divided by 75 plus 112. We get 4.94 meters per second. So the velocity final equals 4.94 meters per second. So Tyler came in there, barreling through at 8.25 meters per second, slammed into Gerard, hung on to him, and then they were flying backwards at 4.94 meters per second. All right. So this is what we just did was really an example of what's called an inelastic collision. Okay, so these were the two football players we were talking about. So this is what happens when two objects come in and they collide, but then they stick together. All right, in a inelastic collision, momentum is conserved. This is always true in any collision. Okay, and their masses combine. All right. So this is our formula for an inelastic collision. Okay, and it's really just the same idea as conservation of momentum, only our masses are going to be combined over here because it became one object, right? Which is exactly what we just walked through. Okay, so let's do a couple problems here. All right, so we've got a 2.0 times 10 to the 5th kilogram train car moving east at 21 meters per second, collides with a 4.0 times 10 to the 5th kilogram totally loaded fully loaded train car initially at rest. The two cars stick together, so we've got one guy here, and he's 2.0 times 10 to the 5th kilograms, right? And he's going this way at 21 meters per second. And then he hits another guy that's 4.0 times 10 to the 5th kilograms, right? At 0 meters per second, right? And the two cars stick together. Okay, find the velocity of the two cars after the collision. So really we can just jump straight to our formula. We know that m1v1i plus m2v2i is going to be equal to m1 plus m2 times vf. Okay, so m1, we'll just call this one 1 and this one 2, just to make life easy. So m1 was 2.0 times 10 to the 5th. Times our initial velocity, which was 21, times m2, or plus m2, which is 4.0 times 10 to the 5th, times 0, because we have a 0 initial velocity for that guy, and then we're going to divide it by m1 plus m2. So that'd be 2.0 times 10 to the 5th plus 4.0 times 10 to the 5th. And that's going to be equal to our final velocity. All right, so this is essentially what we just did when we were doing it all in one step. So 2 times 10 to the 5th times 21. All right, and the other one goes to 0, and then we're going to divide it by our new total mass, which is 2.0 times 10 to the 5th plus 4.0 times 10 to the 5th. We get 7, just straight up 7. So, whoop, I just threw my calculator on the ground. I'm going to need it in a second. All right, so because our car was going to the east originally, we can infer that this final velocity is also going to the east. So it'd be 7.0 meters per second east. All right. So that's the final velocity of our new massive thing here. Okay. So let's calculate, and it says now calculate the kinetic energy of the two cars before and after the collision. Was the kinetic energy conserved? All right. So initially, the kinetic energy of car 2 is equal to 0 because it's got a 0 velocity. All right. The kinetic energy of car 1 initially would be equal to 1/2 mv squared. Okay, so 1/2 times the mass, which is 2.0 times 10 to the 5th, times the velocity, it's 21 squared. So the kinetic energy initially would be 0.5 times 2.0 times 10 to the 5th times 21 squared. We get 4.41 times 10 to the 7th, but only 2 sig figs. So 4.4 times 10 to the 7th joules. All right, so that's our initial kinetic energy. Our final kinetic energy would be equal to kinetic energy 1/2 mv squared. Okay, and so it would be 1/2 times the new mass, which is 2.0 times 10 to the 5th, plus 4.0 times 10 to the 5th, times our new velocity, which we just found, which was 7.0 squared. All right. Hopefully I get the same thing. So we get, or the same thing I got earlier, 0.5 times 2.0 times 10 to the 5th plus 4.0 times 10 to the 5th times 7 squared. And we got 1.47 times 10 to the 1, 2, 3, 4, 5, 6, 7. So that would be 1.5 times 10 to the 7th, which is what we got earlier, thank goodness. 1.5 times 10 to the 7th joules. So you look at this, no, we lost kinetic energy, and kinetic energy was not conserved. Initially we had this much kinetic energy going in, and then finally we had this much kinetic energy going in. Okay, so it brings us to another important point about inelastic collisions. When you have an inelastic collision, your kinetic energy is always less after the collision. That's because your mass is greater. Okay, this extra energy, or this energy that's lost, gets turned into other forms of energy. It can either be internal energy, the temperature is increased to those two things that ran into each other, or the sound energy, their air is forced to vibrate. So you imagine two train cars that run into each other, it's going to make noise, right? So especially if one of them is going 21 meters per second. It's going to make quite a noise, okay? And so that energy that you hear, that sound, that's actual energy, okay? So anyway, so that energy gets lost, okay? So so you could either have the kinetic energy remain, some of it remain after the collision, or it may all be lost. Just kind of depends on what's colliding and how fast they're going, etc. All right. Now that's an inelastic collision. Elastic collisions are when two objects collide and then they bounce off each other exactly how they were. So like think about like billiard balls, like two billiard balls that hit each other, and they bounce off. That's an elastic collision because the billiard balls don't stick together, right? So that's an elastic collision. Okay, now these are different because kinetic energy is always going to remain the same after the collision. Okay, your kinetic energy doesn't get lost. All right. So perfectly elastic collisions satisfy both of these laws down here. So this was our momentum. Okay, momentum, and then this would be our kinetic energy. Notice that we've got 1/2 m1v1i squared, so that's the initial kinetic energy of the first object. This would be the initial kinetic energy of the second object, is equal to the final kinetic energy of the first plus the final kinetic energy of the second. You really got to get used to being able to read these formulas with these subscripts and infer what they're talking about here. All right, last little bit here. Oops. All right, so two billiard balls collide head-on as shown. Which of the following possible final velocities satisfies the law of conservation of momentum? All right, so law of conservation of momentum, we've got to figure out what our initial momentum was. So our initial momentum is going to be equal to m1v1i plus m2v2i. But our m2, so that we'll just call the red ball 1 and then the yellow ball 2 just to make life easier. Okay, so we know this guy because this is 0. Our second velocity is always going to be equal to 0. So really our initial velocity is always going to be equal to m1v1i. All right, so in this case it would be 0.35 times 4. And so 0.35 times 4, we get 1.4 kilograms, 1.4 kilograms times meters per second. All right, 1.4 kilograms times meters per second. So that's our initial momentum. And now we just got to see which of these three, okay, we've got three different sets. We got a final velocity of A and final velocity of B, and figure out which of these three things match it. So our final momentum, okay, our final momentum is going to be equal to m1v1f plus m2v2f. Okay, so in this first case, okay, so we'll call this case A, B, and C. Okay, so in case A, our m1 is going to be 0.35. All right, times our initial velocity. Oh, you know what? Because M1 and M2, let's simplify this a little bit. So M1 and M2 equal each other, so we can pull that out. So we'll just call that, we'll pull those guys. So M is equal to V1F plus V2F. All right? So anyway, so 0.35 times V1F, which is 2.0. Oops, oh my goodness. 2.0 plus 2.0. Okay, so that becomes 0.35 times 4, which would better get us exactly what you got up there, because that was 0.35 times 4. So that would be 1.4 kilograms times meters per second. And so really you can look at the second one and see as well, well, if you add 0 and 4, that's also going to give you 4 in the middle. So B is also going to be equal to, so it would be 0.35 times 0 plus 4.0. So this is also going to give us the same answer, 1.4 kilograms times meters per second. So far A and B are both valid resultant velocities. Okay, and then our C value here, well, I can't do this one in my head as well, so I'll say 0.35 times 1.5 plus 2.5. Okay, so 1.5, well, I could have done that in my head actually. So that equals 4.0, so that's 1.4 kilograms times meters per second. All right, so all three of these things are valid. All right, this next one we do with kinetic energy. We got to see if our kinetic energy is conserved. So we got to find our initial kinetic energy first. All right, so our kinetic energy initially, okay, is equal to 1/2 mvi squared plus 1/2 mv. So this would be mass of 1i m2v 2i squared. Okay, so this is all going to be 0 because we have 0 velocity again down here. Okay, so really our kinetic energy initially is going to be equal to 1/2 times the mass of our ball, which is 0.35, times the velocity, initial velocity, which is 4.0 squared. All right, so 0.35 times 16 divided by 2 is equal to 2.8. 2.8 joules. Okay. All right, so that's our initial. Now, if the conservation of kinetic energy is held true, that means each time we calculate the kinetic energy of these guys, we should get the same value here. All right, so kinetic energy final will be equal to 1/2 m times v1 final squared plus 1/2 m v2 final squared. Okay. Now let's pull out the 1/2 and the m. So it'd be 1/2 times m times v1f squared plus v2f squared. All right. So then we just have to plug these guys in, all three of these values. So it'd be, so for A, I've run out of room here. So A here, A would be equal to the kinetic energy of, maybe we'll label it a little better. Kinetic energy of A would be equal to 1/2 times 0.35 times V1F, which would be 2.0 squared, 2.0 squared, plus V2F squared, which would be 2.0 squared. All right, so that becomes 8.35. So 0.5 times 0.35 times 2 squared plus 2 squared, so that's 8 times 8. So we get 1.4. Yeah, so 1.4. So this doesn't hold true. So this guy, no good, right? It will say A, B, C. So this guy doesn't hold true. All right, let's try kinetic energy of B, right, of situation B here. So this would be the same start, 1/2 times 0.35 is equal to our initial, so that'd be 0 squared plus 4.0 squared. So it'd be 0.35. Well, and that you can already tell. Well, I'll just go ahead and do it just to prove it. 0.5 times 0.35 times 16, and get 2.8. Okay, so 2.8 joules. All right, so that's good. This one's valid. B is valid. Situation B, the second row here. And then we'll try kinetic energy of C. All right, so that would be the same start, 1/2 times 0.35. And then in C, we'd have 1.5 squared plus 2.5 squared. All right, so we have 0.5 times 0.35 times 1.5 squared plus 2.5 squared. We get 4.4875. So we'll call it, 1.4875. So we'll just call it 1.5 joules. So that one's no good, right? So only this row is the good one. Cool. So anyway, so that's part 5. That's the end of the unit. You made it all the way through the end. I'm proud of you. Do some practice problems. Take that last checkpoint, and you'll be good to go. Ask me if you have any questions.